Hello, everybody. Welcome back to another edition of zkStudyClub. Today is going to be a little bit special because we have not one, but two sets of authors and two papers on a similar topic that we'll be presenting here today. And so without further ado, I'll let the authors introduce themselves, and then we'll go one after the other, present this work, and have a conversation about this topic of proximity proofs for Reed-Solomon codes. So with that, Ben, I'll let you and your team introduce themselves, and we'll pass it over to Alistair and Elizabeth.
Sure. So I'll start. Yeah, Ben Diamond. I've worked in cryptography for 7 years ish. My origins were in pure math, and maybe going back into that a little bit these days. So experimenting, working in a lot of different areas right now. So yeah, that's all I got.
Cool. I'm Angus Gruen. My origins are also pure maths. I get the sense that this might be a common theme of the authors. I've been working in sort of cryptography for about 3 or so years. I guess I'm one of the main people working on Plonky 3, so sort of developing these very low-level libraries for use by lots of teams.
Awesome. Go for it, Alistair.
Hi, I'm Alistair. My background is theoretical computer science rather than maths, but I did learning theory, so I'm kind of comfortable with this probability stuff. And my path to cryptography went via blockchain. I've been working, on Polkadot for 6 years. And in the process of doing blockchain research, I picked up lots of cryptography. That's me.
Hi, my name is Elizabeth Crites. I'm also working at Web3 Foundation with Alistair. We've been working together for about 2 years, mostly on stuff for Polkadot, also some threshold crypto, which I'm going to talk a little bit about, which inspired this work. My background's also in math, but PDEs, so kind of unrelated. I came into cryptography kind of halfway through my PhD. Yeah, that's it for me.
Okay, awesome. Thank you guys so much for your intro. And like I said, we're gonna, because of the special 2-team format, we're gonna start with the presentation by Ben and Angus, and then we've got some content from Alistair and Elizabeth too. I think we're just gonna kind of see how it goes in terms of questions that you guys have in the audience, and where the discussion leads. But with that, thank you all for being here and taking the time, early or late, depending on what time zone you're calling in from. And yeah, Ben and Angus, please take it away.
Okay, cool. I think I was going to start. Ben and I might jump back and forth a bunch, and then also I think Alistair and Elizabeth might jump in. So we'll sort of just see what feels good. I guess we want to start off by giving a little bit of background for the problem. I'm assuming, I guess we're sort of assuming a relatively high level of background already. Sort of, we're hoping that people have some sense of what this problem is already, but we wanted to just sort of show a couple of slides to try and at least jog the memory of exactly what this problem is talking about. So what are we dealing? So we're dealing with linear codes, and so I think the way that you visualize linear codes probably depends a lot on exactly sort of what you're using them for. But at least for Ben and I think this will sort of come through in our talk. The nicest way to visualize them is sort of this picture we have of, you can sort of imagine a larger space. So here we have 3 dimensions, but in general you have many more. And your code subspace is this sort of line of distinct points. And this picture is a little bit misleading because, of course, this is sort of working over the real numbers. It makes things look continuous, whereas in reality we're working over finite fields. But in practice, this is a reasonably good picture to keep in mind if you have these sort of isolated points that have some distance between them. And very much what Ben and I's work is about is sort of taking these points and sort of blowing up these balls around each point and asking sort of how big is the intersection? Well, firstly, how big is the ball? And secondly, how big is the intersection? But then more than just linear codes, what we're interested in is Reed-Solomon codes. And so Reed-Solomon codes are a pretty special type of linear code that basically rely on this quite nice, oopsies, okay. Sorry. So we would call the beat space the word space, and then the code subspace the code word space. And this comes up as sort of when we're picking words and similar. Okay, so we mostly care about Reed-Solomon codes, and what Reed-Solomon codes rely on is this very, very nice sort of bijection between polynomial coefficients and polynomial interpolations. And so this is sort of the degree 2 case. It's sort of well known that if you have a polynomial of degree 3, it's uniquely determined by 2 points. But more generally, there's this sort of famous statement that if you have a polynomial of degree less than k, it is uniquely of degree k minus 1, it's uniquely determined by k points. And this basically lets us construct these codes where our subspace are evaluations of these low degree polynomials. And these turn out to have a whole bunch of really nice properties that I'll very briefly get into. So to give some sort of actual, I guess, symbols, we're going to fix our finite field at a subset and then fix an integer. And so the Reed-Solomon code, it depends precisely on what is the size of this subset D, on what is the structure of the subset D. But for actually Ben and my work, and I think also for Elizabeth and Alistair's work, it actually doesn't matter. So in general, the codes depend on this D, but for us, we can just sort of ignore this and instead just have an integer here. And this actually won't give us any problems. And so then our code word space is the set of evaluation vectors. So basically you assign some element of F to each point in D. And so you can sort of easily see that the number of different, the size of our code word space is n to the power of F. Where here the size of F, I guess, should be Q, but that's fine. And similarly, our code subspace is going to be basically we take polynomials of low degree, so degree less than our fixed in K, and we look at the evaluation vector of those polynomials. And you can easily work out that the number of code words is sort of this much smaller factor. So you can sort of take a ratio here and see that assuming that K is a lot less than N, most things aren't code words. Yeah, Elin?
Wait, so is this a typo? Is the first thing supposed to be word space rather than code word space?
Yeah, sorry. I think Ben and I were working on these. Yeah, so you're completely right. I'm sorry. Yeah. I guess you can sort of, I guess this is the word space, I suppose, in sense it's the larger space where the code words live. But I think based off the previous slide, this should be I'm sorry. So the first one is the full set of points of the whole space and the code space subspace, and you can see that if n is bigger than k, most points are in the are not in the code subspace. In fact, the vast majority are not. And so one of the most important aspects of codes that we care about is this sort of distance property, so the Hamming distance. So what is the Hamming distance? The Hamming distance just says how far apart are sort of two evaluation vectors. So you can see here we have sort of two strings, and these would have Hamming distance 3 because there are 3 points they differ at. And in particular, we don't care about, say, how big the difference is. So you sort of the fact that this is like 8, 6 is a difference of 2, whereas the others are a difference of 1 is immaterial to us. We just care how many points do they disagree at. And the reason the Hamming distance is very interesting is that for Reed-Solomon codes, you have these naturally very large Hamming distances. So in particular, because a polynomial of degree less than k is uniquely determined by k points, so there are two statements. So firstly, the minimum distance between code words is going to be n minus k plus 1. And the way to think about this is this turns out to be equivalent to the question, how many zeros can a polynomial have without being 0? And by our statement up here, we can see, well, you can have at most k minus 1 zeros. Once you have k zeros, then this uniquely determines your polynomial, and therefore you have to be 0. And so you can have at most k minus 1 zeros, which means that the minimum distance to the minimum Hamming distance to the 0 polynomial is n minus k minus 1, which is this thing. And this means that we have the unique decoding radius, which is n minus k on 2. There may be a factor of there might be some minor plus or minus 1 errors that I apologize in advance for. Or Ben may have gone through and fixed this.
It's good.
You fixed this? Okay. I think when I initially wrote this,
this is true if n and k are even. If it's not, maybe you need something else, but it's fine as written.
Great. But the point of the unique decoding radius is that if your distance to a code word is less than n minus k on 2, then you can only be close to a unique code word. And this is actually the region where lots of our proximity gap results are, I wouldn't say easy to prove, but easier to prove. Sort of while you're in unique decoding, things just sort of work. And then outside of this, you've got called list decoding, where all of a sudden you have to worry that you might be close to multiple code words at once. The other thing to note about this definition that you get is you not only get a minimum distance, you also get a maximum distance. And indeed, the maximum distance of any point to the code is n minus k. And this is firstly a little bit strange. This is actually smaller than this minimum distance that I read up above. But the key thing to note here, of course, is that any code word actually has distance 0. So the fact that like code words are far apart, if you take something that isn't a code word, it actually turns out that it can be at most n minus k. And the reason for this is exactly this same statement above of you can just pick k locations and that defines a polynomial. So that is in the code. And so you can always find a polynomial whose distance is at most n minus k. Okay, and this I guess is what we call the capacity, because this is where basically all proximity gaps results become meaningless because everything's close to the code. Technically, they still become true. They're just vacuous. Okay, I think I'm jumping to Ben for a bit.
Yep. So let me try to take over.
I can stop sharing.
Okay, I think we should be good. Do you see proximity gaps?
Yeah,
Okay,
yeah.
so yeah, let me just keep running, pick it up where we were. So our result is about a phenomenon called proximity gaps, which sort of sits on top of coding theory, but is really a kind of really a canonical coding theoretic phenomenon. Okay, so here's a very abstractified code. Okay, so this box is the word space, and these 3 dots are the code words. And as Angus said, we're interested in what happens when we blow up a ball of varying radius around each code word. Here you can see the balls don't intersect at all. This picture you can think of as unique decoding. Eventually the balls will start intersecting, and here's a picture of so-called capacity. Okay, so at this point the balls completely fill the space. This is the radius such that every word is within some ball. So this radius turns out to be n minus k, just like Angus just said. Now, proximity gaps is a question about how lines can interact with the union of these balls. So essentially, if you're within the blue, it means you're close to the code, is what we call it, close to some code word. Of course, which code word you're close to depends on which circle you're in, but what we're interested in is the union of all blue circles. So to be close to a code word, doesn't matter which one. Now, if I draw an affine line, that line, a couple things can happen. It can consist entirely of close points. It can live entirely in the blue area, or maybe none of it can, or maybe a small amount of it can. And the other thing that can happen is some non-trivial proportion, like let's say half. Okay, what proximity gaps means is that we like these 3 on the left. We don't like this. We say that a code has proximity gaps if these 3 things can happen and this one can't. That's kind of what we're after. Now, there are 2 parameters that are important. First is what is the radius around the balls, and the other is what is the proportion that we allow to be covered. If that proportion isn't 1, it should be something small. And then what is that small thing? I like to think of that as the false witness probability. It's the probability that a line that isn't close, it's the proportion of the non-close line that consists of false witnesses to the closeness of the line. Okay, now one important thing we do in our paper, and actually literally the identical same theorem was stated and proved by Elizabeth and Alistair, is that proximity gaps are related to the kind of generic covered proportion, right? So we want to reduce the problem of proximity gaps, which is about affine lines, to something even more fundamental, which is how much of the word space is covered by the blue balls. And the way we do that reduction is by using what's called a deep hole, which is a point, a word that is as far as a word can be from the code. That's this little red point here. And the idea is that if too much of the word space is covered by the blue balls, then a line, we must be able to pick a line that commensurately hits that mass. So it couldn't happen that the mass was very large, but every line missed it, right? This is a kind of classic averaging argument. Okay, so jump into this slightly more technical part of the talk, and we're very time limited, so I'm just going to blast through this as quickly as I can. So this is the conjecture from BKICS 23 that we disprove. So what this line sweeping argument shows is that if this conjecture were true, then this would also be true, right? Pick a z, pick a radius that's less than the covering radius, then the proportion covered, the proportion that's close to the code should be bounded from above by this polynomial expression for some exponent c star. So we show that this can't be true, and for which z? So in a way, it becomes more impressive if you disprove this even for smaller z, not just n minus k minus 1, but even smaller things. And we do disprove this for z that drift away from n minus k minus 1 by an unbounded function, and also our k is unbounded. So this is a bit more technical, but this is effectively what we do prove in our paper. Just to clear some terminology, so as Angus said, this is the covering radius, aka capacity. What we're going to do is pick a ball radius z that is less than capacity, and so here's our proximity parameter, ball radius, same thing. It's convenient to give a name to this guy h. H is how far z is away from n minus k. So what we want to do is disprove it, not just for any old k and h, but ideally for as large a k and h as we can. And indeed, we do get k and h, something like n to the sort of a little bit less than root n to the 1/2 minus epsilon, something like that. So I think Angus was going to take over again here. Is that correct?
Yep, I can jump in.
Yeah. So just.
All right, can I steal it from you? Wait, try this one. Okay, attempt 2, it's back.
Start, Angus, maybe just a good, since it's a natural
Yeah.
hesitation. Does anyone have any questions up to this point for
Sure.
Angus on the presentation? All right, here's someone unmuting, but I'm not sure if they have a question or they're just unmuted. Okay, cool. All right, Angus, you're going to proceed.
Okay, great. Okay, so I think one of the nice things about this result that I'd like to try and get through to people is that there is actually, it's possible to really see what's going on here intuitively. So I think Ben in a moment was going to go through, we'll go through the maths of how we actually get this, how we actually prove this rigorously. And of course, you know, you don't want to mistake intuition for proofs. But I think very much, if you asked, like, why do we think this is true, ignoring the proofs, I think there's sort of some very nice pictures you can get by looking at how this theorem behaves in some sort of special limits. So in particular, what we want to think about is what happens when you take Reed-Solomon codes and set k equals 1. So k equals 1 means that the degree of our polynomial has to be less than 1, i.e. has to be 0, i.e. our polynomials have to be constant. And so that means our code words just look like so-called repetition codes. So you can see here our code words are just some value repeated for the whole code. And in this special case, sort of everything gets simpler. So if we take a random word, let's define this sort of repetition R of u to be the maximum number of times that anything repeats. Then the distance from our random word u to our Reed-Solomon code is exactly n minus this repetition. And so we can take sort of two limits. We can say we set k equals 1, and we can also set our shortfall h to be 1. And so now what happens is, well, what does it mean for something to be n minus 2 away? Well, it says, what's the probability that 2 of u's entries are identical? And this is actually a restatement of a reasonably famous problem. This is exactly the birthday paradox. And I guess this is maybe one hint already that maybe sort of these shortfalls aren't too hard to come across, because I think the key point of the birthday paradox is that it's more likely to have these matching birthdays than you might expect. And really this is sort of what's also going on here. That sort of it's more likely to get these sort of close points than I think the community sort of naively expected when we sort of first wrote down these conjectures, or at least first worked with all these conjectures. There's one other thing that we want to do, which is kind of makes it easy to estimate, and this is sort of this is a slightly technical assumption, which just turns out to sort of very nicely capture what's going on. So this is our ground truth. So what we have here is, you could imagine each of these balls, there's sort of a code word at the center, and these are like the balls around the code word. And what we're trying to measure in this random word situation is, what is the probability if we drop a random word in this square, what's the probability it lands in one of these balls? And we can restate this in this sort of totally slightly bizarre way, where we say, okay, what about instead, what if we drop lots of different random words, lots of random words in, but only ask about a single ball? And you can ask, well, how do these two probabilities relate? And I mean, if anyone has any guesses, you're welcome to say them now.
Are they the same?
So not quite. That's a good guess. The answer is the answer is basically yes, but for various limits, sort of the ground truth will be a little bit higher or a little bit lower. So in particular, one reason that you can expect the ground truth that these can't quite be the same is that if our balls are small enough that we're in unique decoding, then we know that actually no point can land in two balls, and so you end up with this. You end up that the independence has to be overcounting. Sorry, has to be is undercounting. It's a little bit too low. Sorry. On the other hand, as your rate approaches capacity, then we have these huge intersections between our balls, and our independence ends up being a little bit high. So it goes up and down. But the key point here is that, as you can see on this graph, so this is basically the probability of getting, this is the birthday paradox roughly. This is the probability that you have two people who's with the same birthday, where on the x-axis we have sort of the number of people in the room, and we have sort of three things here. So in this nice case, we can actually compute the true probability. We can't all usually do this, unfortunately, because it's a little bit complicated, but at least here we can. And then we also can compute what happens if we use this independence assumption, and what happens if we use this independence plus this Poisson assumption that is very useful for actually making visualizations. And the takeaway from this graph is that these lines are basically identical. Like, you can sort of see that there are places where there's a little bit of difference, but it's never more than 1 or 2%. So sort of the information you get by staring at, say, the independence and Poisson graph covers basically everything you might want. Like, it gives you a very good intuition for what is actually going on in reality. And so then you can say, well, so far we've looked at this n equals 2 case, but how do we generalize from this? So the first thing we might want to do is basically consider what happens if we ask for more than 2 birthdays to be the same. We could ask for 3 or 4 or 5. And so then you can get plots a bit like this. So what's happening here is we're plotting various shortfalls, and these lines are basically corresponding to the probability of finding, the percentage of the space covered by balls of the radius z. And you can see once again, as n rises, sort of for each of these lines, sort of this red line is sort of the birthday paradox. This blue line would be sort of the generalized, like a triple birthday paradox, where you have 3 birthdays on the same day. The green would be 4 birthdays. But you can see that these are actually, these go to 1 sort of relatively fast. And this is even only in the k equals 1 case. And so, like, as you see here, like if any, so here our Q is only 365, so n being 313 is maybe a little bit unrealistic, but we can see that like as n gets large, what you find is that a lot of words actually have quite a lot of these duplicates. And the sort of interesting case is that when you start making k bigger, what you find is this gets even more pronounced. So when k is 60 here, there's sort of two features about this graph. Firstly, you'll note that our shortfalls, as opposed to being like 1 to 5, are now sort of 20 to 30. So our shortfalls are getting much larger, which says that our balls need to be much less big before they're still covering the whole space. The other thing you might notice is that these graphs end up looking basically like step functions. So as n increases, sort of the percentage of the percentage of the space covered by these balls as n is increasing looks like sort of 0, 0, 0, 0, 1. And so trying to estimate where this where this sort of step is a very good indicator for where these sort of random techniques are going to start working. And so yeah, in particular, if you stare at this graph, you can see if n 134, and so note here, like as opposed to in the last case where we had to take n up to like 300, here n's only 134, but most words are more than 20 close to the code. And here 20 compared to 365 is like a reasonably high percentage. Obviously, these graphs all change a bit as Q gets larger, and so Q being 365 is a little smaller than anyone would use for a zero knowledge system. It's also unfortunately not prime, but you could actually make these same graphs with Q much, much bigger, or you can sort of start to compute things numerically. And yeah, again, once again, if we get n to be similar to where we were before, our words get very close. Okay, so basically what this comes up with is that we can come up with a sort of the following linear graph for what's going on. So let's lock in our row, and we can first work out where is our unique decoding. So this is the section where proximity gaps is just sort of solved. This section works very well. Indeed, we actually know it's to be true in a slightly larger section, which is list decoding. So here the blue section is where you have this situation that you might be close to more than one code word, but you're still not close to too many code words. Things work quite well, and this sort of cuts off at this 1 minus root row, because this is where some particular work by Guruswamy cuts out. I mean, this was sort of the original Eli Ben-Sasson et al. Paper about proximity gaps. Similarly, we know that there's no hope of getting proximity gaps past capacity. So once you get to capacity, proximity gaps are sort of immediately vacuous, just because you can't find any points far from the code, so there's nothing to say. And so basically, the proximity gaps conjecture has been about this sort of this region. And what we've sort of shown is that there is this cutoff. So this value below, basically, this is the estimate of where these step functions are occurring. And so in this case, it cuts off, a small segment of the space where it basically says that we can't get proximity gaps past this point from these random words arguments. And to be clear, this is a little bit more of the space than we explicitly show. We have a proof that requires some technical details and so only works up to these sort of cube root ends, not this sort of log behavior. But I think it's sort of reasonable to expect that this holds a bit further out. And I think actually also Elizabeth and Alistair's work gets closer to these sort of thresholds.
Yeah. So
the other, sorry, you go.
Yeah. So this expression log 2 e of a row times a row, I'm not sure that it's tight. Because the naive thing gets you something more like h2 of row, which is at a half or at a small thing closer to log 2 over row than e over row. And somehow you seem to be slightly out here, which is odd because you did all this stuff to much greater detail than we did.
Yeah, I'm not sure. It may be. So I think we did some stuff to very high detail. I think some of the the estimates, we sort of played a bit fast and loose, because I think we originally had the paper up and someone immediately asked us, hey, what does the values look like in real world settings? And we're like, oh yeah, we should try and write something for that. But yeah, I'm not sure. I certainly agree that this bound is a bit loose. Is probably somewhat loose. It's not clear to me exactly how loose it is. I think
So
the tough.
H2 here is very close, and this is very close to the classic Curie entropy estimate.
Yes.
And this is a bit higher than that, which is the problem if you're trying to have a bound it. Yeah.
So maybe,
Yeah.
I mean, it might be kind of interesting. Sorry to take a little improv here, but I mean, Alistair, given this potential difference between these two thresholds between your work and theirs, maybe this could be a good jumping off point into covering a bit of your work. I want to be conscious, Angus. I know you were like on a roll there and you have other stuff, but I do think it is kind of, given this is a point of difference potentially, or at least a point of conversation.
I don't know. Maybe Angus can carry on. This is we still have.
Yeah, we got plenty of time too. Okay, so maybe we'll do that. We'll put a pin in that and come back to this point. Any other questions for Angus and Ben at this point in the presentation? Cool. This is great. Keep going, Angus.
Yeah. Okay, great. I'm actually about to hand off back to Ben. I've sort of done, but I guess this is the final slide I want to show a bit. And so this is basically what happens if you take that previous slide and just look at different values of rho. And as Alistair mentioned, so this red line is sort of the region that we've sort of cut out. As Alistair mentioned, it's possible that this red line is not quite the right one. You might want to have something a bit closer, but unless I'm missing something badly, it shouldn't look massively different. My sense is it should be similar. It's sort of it's small. It's a relatively small difference, unless I'm misunderstanding that. And so what does this show? What does this show? Well, here we're basically plotting rho against I think it's eta. Yeah, rho against basically eta, and our green region is unique decoding where things work well, and our blue region is this 1 minus root rho. So this is where we have proximity gaps proofs, and we sort of know that we have proximity gaps for Reed-Solomon codes. The black region is capacity where everything's doomed, and so this white region is sort of the remainder of what is the conjecture actually asking about. And essentially, what Ben and mine, and then also Alistair and Elizabeth's work shows is that you can't, there's no way we can cover in this whole white region with sort of with a good color. That there is some sliver of this white region very near to capacity, which is just impossible, precisely for the reason that actually you get to the point where most of your code words are close to your code well before you get to capacity. There's sort of not this like smooth, or this, we don't have these steps at capacity. On the other hand, actually, it is true if you let your Q be really, really large. So you can see here we have this log 2Q on the bottom. Even if you use these other formulas, you get something similar. If you let Q be really big, like super exponential in N, then you actually can go up to capacity. So this was a recent paper of Guruswamy and Royale, which said that actually you do get proximity gaps up to capacity, provided you're willing for your Q to be sort of super exponential in N, which is unfortunately not particularly relevant for crypto purposes, but is interesting from a mathematical perspective. But very much when this isn't true, when your Q is large, but not sort of unbelievably large compared to the other variables, what you find is that you have this sort of little carve out you have to take out where you simply not going to be able to get any proximity gap results past this point. Now I'm going to hand over to Ben, who's going to talk about some of the more technical aspects of things. I guess this will also be a decent point if there's anything intuitively that Alistair or Elizabeth want to share or chat about before we sort of jump into the more technical parts of the work.
No, our plan was to do the technical bits after you do the technical bits, and then go back to untechnical bits at the end.
Okay, excellent. It's like a sandwich.
Nice. We'll do 2 talks in opposite order. One will go top to bottom, the other bottom to top. So that's great.
Lovely.
Okay, so I think we're getting a bit squeezed on time, so I might have to just kind of speed run this. Does that sound right?
Yeah, give it. I'd say if you have the next 10 minutes, Ben, take the time within the 10.
10, sure.
Pull the context that was set. I mean, that puts you guys at 45 minutes, and then you guys had some context too. So I'm hopeful that with that, Alistair and Elizabeth can take what time remains, which is almost half, to take it back. And then hopefully if folks have questions, they can just ask them throughout. Hopefully that's okay with the audience. And folks in the audience, please do ask questions if you have them, and also feel free and put them in the comments if you'd like, and I can read them. All right, go for it, Ben.
Okay, great. Well, let's do this. So I think the moral of what Angus just said is that if you believe the independence assumption, you should already be convinced that this conjecture is just not true, right? Because these really nifty Desmos charts were computed with the independence assumption, right? That is what let us compute them so exactly. Now, the real world is more complicated. You have to actually deal with intersections and things like that. But if you do make the independence assumption, you just need to know the ball volume. And then we use the Poisson approximation for that, and that's how we got these. So if you believe those two things, this conjecture is toast. Now, just by looks, you can see how close they really are. But sort of the main body of our paper involves not making this assumption, but actually proving sort of rigorously that the union of these Hamming balls is sort of large, even for radii that are much less than covering radius. So what I'm going to be saying now is sort of the rough sketch of how it is that we do that. So our goal again is a random word close to the code, meaning is it contained in the union of a bunch of balls of radius z, where z is prescribed. So the first step that we do is this kind of inclusion-exclusion trick, right? So if we're interested in the volume of a union, we can lower bound that volume by taking the kind of brute sum, ignoring overlaps, and subtracting these kind of pairwise intersections. And this will give us something smaller than the truth. Now, if even that's big, then we've done what we need. So we actually just essentially take these one at a time. The first thing we turn to is the ball volume. If we have that, we just multiply that by q to the k, and we get a first order estimate. To do that, we do a bit of math. As we say in the paper, the main idea here is something like how the Poisson approximation of the binomial distribution gets derived. We get this really sharp estimate, which is better than the classical one, essentially because it's better and worse, right? So what this fancy notation means is that if you take the ground truth here and you take our expression here, they might not be close, but they can be made close. So whether they're close or not will depend on what z, n, and q are. For some z, n, and q, they might be way off, but if we choose z, n, and q such that these expressions get small, then the ratio between the ground truth and our estimate will go to 1, right? So it's a controllable.
How bad this last number looks?
Wait, say again?
Why is this thing not bigger than 1? M minus z squared z over n squared.
Why is it no bigger than
this is where our condition about like n minus z being sort of O of n cubed comes from. This is like
oh yeah, so we need z to be nearish to n, right? Z should be something like n minus cube root of n or something.
Hang on, but isn't z the number of errors?
Z is the
z is the ball radius.
It is. It's the
It
radius.
is, yes, but aren't we talking about n minus k here, or what is n?
K is also small. K is also growing like cube root of n. So
you need k to be small to make this work.
K, well, not yes, relatively small. K needs to be something like cube root of n, and z will n minus z will also be a constant factor difference from k.
Why would k be cube root of n? Don't people use codes with like k is equal to?
Well, that's kind of the point, right? So our counterexamples require rates that go to 0 and also shortfalls that go to 0, relative rates and shortfalls.
Interesting, because I think ours don't. Okay.
Your k can be, your rho can be constant, but your shortfall goes to 0 like ours does.
Yes, the shortfall goes to 0.
Yeah, so that's a nice feature of your proof, for sure. By the way, I mean, like, k being a constant proportion of n is not required by the conjecture, right? So not even if for k equals 1, you could already disprove the conjecture that way. Although again, our k's do grow to infinity, just more slowly than n does.
Right, it's just a constant factor of n, sort of k is equal to n over something, is what I'd expect the parameters people would use in snarks in practice, and we try to stick to those, even if they don't make sense for our thing.
No, yeah,
Okay.
I agree. It's nice if you can disprove it for constant k, constant rho. That's nice. We didn't, like in our rigorous portion, but yeah. Maybe our techniques could be adapted. We're not sure though. So should I carry on?
Yeah, go for it. And Alistair, just to pin in that, I mean, I think one question that naturally comes up, at least in my mind, is, yeah, I mean, for real world parameter sets that people choose, it's like kind of where do you what is the takeaway for that, right? So I think this probably gets more to the area that you're going to cover in the light of how you sounds like you did your proof, is like possibly the relevance in terms of picking parameters for these systems and how this conjecture or this disproving of the conjecture impacts choices of those parameters. But yes, Ben, please continue. I promise you 10 minutes, and I'm taking your time by talking. So keep going.
Sure. Okay, so this is a chart that tabulates how our estimate performs for n equal 365 and z very close to n. You can show that actually it does better even than the kind of classical estimate based on entropy does. So I think that's independently interesting that we have a really good ball volume estimate, but it also does prove useful for a proof. So turn to intersections. This I'm going to have to truly speed run, but basically there's a lot of combinatorics here. If I want to understand how two balls intersect, sort of by translation, I can move one to be 0 and consider intersections between 0 and non-zero code words. And moreover, if I sort of scramble V but keep its weight the same, the number of non-zero components, then that doesn't affect the intersection. So it suffices to understand how many weight W code words there are and how big these intersections are. So the one place in the paper where we actually use MDS is where we bound from above how many code words of weight W there can be for each W bigger than or equal to D. To actually talk about the intersection, we need to do a bit of combinatorics. Here's a kind of visual proof of this bound. Our main theorem about intersections basically combines those two lemmas and then does a bit more kind of analysis to show that there's a double sum that comes out containing terms with a kind of multinomial coefficient and then something that depends on Q. For as long as you make these controllers go to 0, then we can show that one summand will dominate this sum, and you get really a quite simple expression here. So here's the ground truth, here's the estimate, and then these are the controllers. Okay, so what remains for us to do is to let n go to infinity, and then for each n to tell you what q should be, tell you what k should be, and what z should be, and to let this thing go asymptotically. Now, k might not be an integer, q might not be prime or prime power. There's a kind of technical, we need to deal with this interestingly goes number theoretic in a way that we didn't expect, but we find to be interesting, just to guarantee that primes or prime powers exist in these intervals. I can talk more about that if people have questions. So our main theorem is that if we specialize n, q, k, and z in that way, then our controllers do go to 0, so our estimates become asymptotically sharp, and the contribution becomes negligible, goes to 0 relative to the first order estimates. So we can certifiably, rigorously throw away the intersections, and the sum term asymptotically outpaces 1 over n, which is kind of the benchmark we need to hit. Since we set q to be n to the c star plus 1, the decay rate to beat is n to the c over q, which is 1/nth. So here's a visual proof of the kind of final accounting. You can see that in the red is the full ground truth. It's so close to the orange you can barely see the difference. Orange is first order, so throwing out intersections. And then finally, we bound this from below in a number of steps. We finally end up with something that sort of on its face outpaces 1 over n. And that's enough to disprove the conjecture. So here, based on our more heuristic analysis, we do suggest a new parameterization. If you want to gain, say, 100 bits of security, then you're going to need more than 100 queries, say, at the rate 1/2 case. And finally, we propose an amended conjecture. I think this is still kicking. I don't think this has been disproven by the subsequent work of Ben-Sasson, Swastik, Ulrich, and others. So we can talk about that too. So I think that should be about 10 minutes. I can call it at this point.
Well, as speed runs go, that was good. Impressive. Thanks, Ben, for covering 12 or 14 pages of proofs in 10 minutes. I don't know if there was enough time there for people to actually get enough to ask questions, but I'll pause in case folks do have questions.
That last conjecture, yeah. So what I would have loved is you have a large enough n, but you never tell us what it is. Everything else is concrete.
Well, here's the thing.
And it makes it difficult.
No, yeah, I would love that too. I would love to know everything. Now we put that there just like in theory, if n is too small, then the very technique of our paper and yours could just make the false witness probability kind of unduly high, right? It could make it sort of abnormally high, and then as n sort of matures and gets big enough, this thing will sort of conform to a more reasonable exponent. So what we want is for implementers to get a C that actually reflects the kind of limiting behavior, not something artificial that happens early on. That's why we did that. Now, we could have tossed out this n large enough condition that wouldn't make this conjecture, that can't make it go from true to false. It's only there so that C can be set in a more sharp way, and same with K. We could have killed both n and k and just said n to the c over q, but that c might end up bigger than it needs to be if we did that, right?
Yeah, of course. But having the issue again is that if n isn't large enough in practice, like people probably use n's that are quite a lot smaller than q's. If their q's are 2 to 128 or something, and their n's are 2 to 20, is big enough. You know?
So actually, I can just maybe a comment here that's useful. So the thing that turns out to be really nasty for this conjecture turns out it's not exactly about n that causes things to be a disaster. The issue is that if you can set up situations where like k equals 1 or h equals 1, then you start to get really, really big powers for sort of basically silly reasons. And so I think you can actually write down what you want for n, and you want n to be large enough such that both h and k are sort of bounded a fair way away from 1. I agree that's sort of not. I think we did have expressions that we wrote down using our sort of heuristic bound at some point, but they weren't super clean.
Okay. Anyway, yeah.
I mean, my response is if you don't like that, get rid of it. The conjecture will keep its truth value. You just might end up with a C that's bigger than you like. And so in other words, what usually happens in real life,
if you don't have a large enough n, it's wrong.
no,
We
just
already-
increase C, just increase C or K in order to
No, increasing
for small n.
there's some. No, so in particular the domain in a subfield case.
Alistair, you?
Was which, you know, with the recent paper of Fenzi and Sasso, it is enough to your large enough n was escaping that, and
So-
if you don't, then it doesn't work.
Oh man, now Dara's got a question. Never get into your paper, Alistair. I'm sorry. Dara, go for it.
Yeah. So, speaking as an implementer and designer, it doesn't matter if the precise expression is not very clean. It just matters that you've got code that can calculate it. So as long as you can write a parameter estimator that people can use that says whether specific parameters are okay or not, then
Yeah,
that's sufficient, even if it's a really nasty and hairy conjecture.
So we put a concrete conjecture in our paper, and 2 papers have come out since proving it wrong. And now we're going to put an updated concrete conjecture. Now you can change the numbers.
Yeah.
I mean, I think at least for us, the thing that we care about more than necessarily this conjecture is, I think if we go back a slide or two, is we do put some concrete numbers in. These sort of query numbers. And I guess this is sort of more of what our concrete, in some sense, statement is. Because I think when we're trying to work out how to fix the conjecture, like I think it's that's one of these things that Alistair pointed out, right, was that our counterexample already works in this slightly unrealistic setting. And so I guess it seems like in order to truly fix the conjecture, you need to start like finding ways to sort of slice away these sort of very unrealistic settings. And I think this has also come up in some of these counterexamples that have come out since our paper. We start having counterexamples which work with very specific choices of like domain sets, which aren't used in practice, and it's sort of can be hard to work out exactly how they relate to.
I'm still hung up on this idea that taking that out could make the conjecture false, right? Like, let's say I'm going to prove that our conjecture implies the version of it with that taken out, right? Like, fix some case where our conjecture holds. Whatever that effective n is, let's say it's like a trillion or like a Google or something, right? Like, surely if you take the cases where n is less than that point, then the false witness probability kind of can't be too large, right? Because it must be at most some quantity that depends on the effective, you know, capital N, like Google. So just let C and K be so enormous that you kind of encompass that, and then let it run, and you should still have the conjecture be true in that case, right? Does this make any sense?
So still, so the issue is C and K can be huge, but they can't deal with this exponential blow up, which you would have got after the list decoding capacity bound. So the issue is how this is a function of eta.
Yeah, like I thought that the thing that was saving us in some of these was that C and K are functions of rho and eta, as opposed to being having to be fixed for all. Like I think that really one takeaway from here is that you probably don't want to. You may well not be able to fix and have the same thing for all rho and eta.
Well, that's
Right,
really not what we're claiming. The whole
Yeah.
point is that RK and RC should change if rho and eta change, right? So
Yes.
if you don't allow that, you're back at square one. You've essentially recovered the original conjecture that we disproved, right? In fact, if you see here how rho and eta must be positive. Like if you eliminate that requirement and let them be zero, you've essentially recovered the classical conjecture. In other words, they have one C that's supposed to work for all rho and eta, whereas we force the code family's rates and shortfalls to be bounded from below by what? Well, by constants rho and eta that you can choose, but your k and your c and your effective n will then change if your rho and your eta change. I mean, that's effectively the whole point of our conjecture.
But here, nothing depends on Q.
No, not on Q actually.
Right.
I mean, there is a minor Q dependence, obviously, in the.
It must be
function.
at least n. Yeah, exactly.
Right.
Alistair,
Yes.
is
Okay. That the thing is that that's not enough. Anyway.
Yeah,
Never
we
mind,
can
maybe-
chat more.
Maybe I can present something
Okay.
before we.
Yeah,
We're an hour in.
let's present. Oh, Justin's got a question. Justin, you want me to say it? I'll give
Is
you a
it fair
second.
to say that the conjecture attack is non-constructive? So
Oh, I have slides on this exact question.
Well,
Yeah.
wow. Look at
our
that.
attack, I think, it should be considered non-constructive. But yeah,
It is constructive in case you can make our attack constructive, and like if you let rho be small, like if you can find situations where like rho goes to 1, then our attack is constructive. Like, and this does turn up in worse situations where rho is getting
In
small.
practice, yeah, I actually think it's still a reasonable assumption that that the snarks under the previous conjecture are actually computationally sound with additional computational assumptions.
Yeah, that's
This we
probably
don't
fair.
know, and the reason for that is this problem of finding these close code works is not something we have an algorithm for.
Well,
wait,
exactly.
yes, you're saying
Unless k is small, right? If k is like 0, 1, like if k is like less than 8 or something, then actually you can do sort of.
oh, sure.
There are weird cases where you get down to small enough things that this maybe is doable, but,
Well, that
but
I'm not,
I think I agree.
because the conjecture is asymptotic in nature. So I don't see how any finite, any single counter example.
We should let Alistair talk. We can come back
Yeah.
to this.
Okay.
Let me,
All right, you've heard way more than you bargained for.
No, it's good. I didn't mean to interrupt you guys, but I do want to make sure. Mainly, I'm just conscious of Alistair and Elizabeth. And Alistair is saying some good points, and I think it's a great discussion. But I want to make sure that we get the other half here, because to round out the picture. So, Alistair, going to you, and I think we're switching to Elizabeth at some point. I guess, Alistair, you just do that when it feels.
let's see if we get anywhere. Okay, I have some slides. Where are we? Yeah, so the first thing that's kind of different is I think that what's going on with proximity gaps is not too different from what's going on with list decoding. And this phenomena was, known about in the 1950s. Coding theory is an old subject. So there is, for a result by Peter Elias in the 1950s, there is some threshold which is below capacity, below which there are some codes that are list decodable, and researchers added more things to this. The original example is a random code that's not even a linear code, so it doesn't even make sense to do correlated agreement. And above this bound, everything has an exponentially sized list. And most of what we're trying to do here is to try and argue that this behavior for list decoding also happens for correlated agreement and these proximity gaps. And yes, just like Ben and Angus, we showed that there was a proximity gap if the proximity gap fails if the chances of a random word being close to the code is too high. So we just need to get the random code. Here is our result of the random a random word at different f. Our f is their z. We get a complicated expression, and which involves this HQ of delta we saw in the list decoding capacity bound. Here's what it is. And it turns out that in some regions, these two numbers aren't that far from each other. But you'll have to trust me on that one because I don't have pretty graphs. And I think we can guess it from the discussion that this probably is closer in more regions than the previous paper's result. even though we thought this thing would be a lot less tight. And yeah, to simplify, okay, we're talking about a difference in rho of about 1 over log q. When the rate is a half, it's very close to 1 over log q, and all of this is very tight. So if you have 128-bit field, it's 1 over 128, and I'm not even sure why this makes too much difference. But that's what we get. So there's the bigger font version. And the technique is basically these list decoding capacity bound analysis worked with sort of Hamming balls, as Ben and Angus explained. We were doing things in terms of disagreement sets, sort of equivalent to the agreement sets. We've seen agreement sets in other results on correlated agreement. And we work with disagreement sets of size f, where the actual disagreement might be smaller than the set, and this means that our approximations end up being wrong if stuff is closer to the word. It's basically if you have lots of things in a list and some of these things are closer than your bound f, then there are lots of disagreement sets. There are more disagreement sets than there are nearby words, and this means we overestimate some things, but makes every formula simpler. But I should rush through all the techniques because we don't have much time. Basically, the thing is counting them with disagreement sets. We want to look at the expectation and variance of this. Just like Ben and Angus's thing, we want to look at the probability of single set of disagreements and intersections, and we don't look at three ways or more because that would just be too complicated. And this probably gives a very similar answer to what you get by inclusion, exclusion up to pairwise intersection, which is what they did. So I'm kind of surprised that, yeah, the answer is slightly different because I just thought it'd be very similar. The nice thing about these disagreement sets is that everything is easy because of Lagrange interpolation. So if you take a random word in one of these sets, well, if you interpolate everything on this domain of size n minus f, you end up with a random polynomial degree n minus f minus 1. And when is this polynomial degree k minus 1? Well, when the top n minus k minus f coefficient is 0, probability q minus n minus yeah, okay, I need a bracket here. This has brackets, right? Q minus brackets k minus n minus f. And there's n choose f of these sets, and this is multiplying quite a small number by a very large number. But at some point, because n choose f can be like closer to 2 to the n, if n minus k minus f is small, then and typically this is going to be bigger than q, and in this region, we end up with this this decoding capacity error. I don't know if any of that makes any sense. Especially not if I try and do this fast as well. Now, when you are looking at the intersection of two of these things, which is, so in other words, we have a random code word, we're looking at two specific sets, and we're asking what the probability over this random code word that these two specific sets, disagreement sets, both have code words that agree with the rest of the word. If the disagreement sets have a intersect by a lot and they have a small union, their union is below n minus k minus 1 plus 1, this is the minimum distance of the code, then the two code words you get with these two things have to be the same. And this is kind of bad for us, but the probability sort of goes down with the intersection is smaller, the probability becomes irrelevant. But the nice thing about
just on the like on the previous slide, that could be q to the minus open paren n minus k
minus f, those parameters, yes.
Yes, exactly. Yeah. Okay.
Yeah, missing the parameters, which missing the parentheses would make the whole thing make sense. Sorry, yeah, that's kind of rough. And the same thing goes on here with this n minus k minus f intersect f prime, same thing. But the nice thing here is that if as it, you know, if these sets are almost as big as, you know, if f is close to m minus k, then these sets are almost, you know, the union of almost all of these sets is going to put us over m minus k, and then these two things are independent, which simplifies the analysis a lot. So in particular, we have this formula for the expectation, and then if you look at the variance, if everything had been independent, right? If we have, you know, the Bernoullis with probability p, then they have variance p times 1 minus p, and we add some independence ones, we just add them all together, and the variance will be smaller than the expectation. But because we had this annoying case where we get the same polynomial, there's this sort of error term, which is this horrible thing. Originally, I had this first term, but then I realized, and it was very great for when Q was massive compared to n. Q is much bigger than n squared. This term is just close to 1 and disappears. And our original application involved cubing an elliptic curve group size. And then we didn't have to worry about this. But in actual people's applications, Q's could be a lot smaller. And n squared can be bigger than Q. And then we had to mess around, and maybe this square root actually gives us something.
Can I ask this min? I don't like mins, I have to confess. So can you tell us, like, what are the two cases represented by this?
Okay, so it really depends on how big this fm minus f over q term is. If it is much smaller than 1, then this first term in the min.
Well, sure. I can see that by reading it off. But
and everything is very close to 1, and this term is almost irrelevant. But if it's big, then you want the square root term. And what's not so obvious is how this compares to n choose f and q to the n to the k minus f. But it turns out that if q and n are the same, then actually this first term in the min would be a constant factor. It would lose you, instead of having 1 over log q, you would get like 1 over 2/3 of 2 over 3 log q. But this square root term saves you and makes it go away when everything's large, and makes everything tight when everything's large. But I don't have graphs showing this, but I believe it's the case.
But like, is it an artifact of a proof step you have where there are, like, let's say 2 different cases that can happen?
Not so much. We had something horrible that looked like an exponential series, but we had a factorial squared in the denominator, and we didn't know how to approximate this. And one thing is just to ignore the square, and then you get the first term. And then you do something cunning and get the second term. No, it's an artifact of the proof. They're not 2 separate cases. But as we get some hypergeometric series that we have no idea how to solve, and like I looked at moment generating the formulas for concentration inequalities for the hypergeometric function and moment generating functions for that. And then there's something called modified Bessel functions of the second kind, and I've got no idea. But I couldn't find anyone who'd actually solved this thing, so I did something brute force. So that's where this thing actually comes from. But then we get the complicated formula and everything's fine. Anyway, and I can explain maybe why we get pairwise independence, but I'm not sure anyone cares, so let's carry on. Conjectures. Okay. So people were doing things based on this eta, which is, 1 minus the rate and error decoding faction. That the analogy with the list decoding capacity result from the 50s indicates that we should just replace this k over n term with this Curie entropy, which is actually within like 1 over log p. Okay, I have p here. of this anyway. And basically, the idea is that we substitute this into the list decoding conjecture and the correlated agreement conjecture and the mutual correlated agreement conjecture, and they're possibly all fine as far as we know. But we first suggested putting in this HQ over N. However, now 2 papers came out proving that this doesn't necessarily work for extension fields. For prime fields, it does work. With HP k over n, where p is the size of the field. And what we believe is true for prime fields when if we're not dealing with binary fields, which we really have no clue about. If you start to have these 2 to the 32-bit primes, then probably what you want is just to have HP where p is the characteristic. And this will lose you 1 in 32, maybe, from the errors, the fraction of errors you can cope with, which is not too bad.
I was going to ask, what should our intuition be for the shape of HP? I know you said you didn't have graphs, but roughly.
Yeah, no, I could have done some great graphs. Like I have a whole load of inequalities for this thing. So HP of delta is approximately, for p being big, is approximately H2 of delta over log p. Log 2p, indeed. And this H2 is this binary thing. It's just a standard thing that goes up to 1.5. It's number of it's the entropy in bits of a Bernoulli, and if that has a half, it's exactly 1 bit, and then it goes down to 0 on either side, including if it goes close, including for rho close to 1. Yeah, in general, HP k over n is close to k over n, like within log 2, and the other difference is this H2 thing, which is unlike things like H2 of delta is greater or equal to 4 delta 1 minus delta.
Is it fair to say that the graph for x equal k over n looks like if you took the graph of y equals x and then you sort of made it a little bit of a bump over that, right? And then if you drive q to infinity, it should get more and more squished and converge to x. Is that a fair statement?
Yeah, if you drive q to infinity, it goes to x. The difference in between it and x
is log 2,
which is H2 over log q.
So in other words,
H2 is the thing you want to have a graph for, and that goes up and down in between 0 and 1.
If I take x, and then I take x plus 1 over log 2 of q, I should get 2 lines of the same slope that will contain the graph of the entropy function.
And in the middle, at a half, very close to a half.
Exactly, it's going to start.
It's going to be
top, and then it's going to go back to the bottom.
The top of these, and it goes down on either side.
If it goes to infinity, these are just going to converge to each other like that.
Sure. We have like a bunch of inequalities in the paper for exactly this reason. Like I have claim 1 or 2 or something is getting a bound on this.
That's what I'm telling. That's what I'm saying now. Is that essentially?
Yeah. So there is a special case, which is one of the things I was trying to discuss for your thing. That well, there are sort of 2 special cases. One is the Kopity-Habok et al. Thing for binary fields. The other is the subfield case. And the subfield case is particularly annoying because it happens all the time in practice. Like, so I think that Euron Jim Posen's Binius uses, if I have a domain of size 2 to 16, you end up with a subfield of size 2 to 16. And this case completely applies to that. Likewise, as Penzi and Sanso pointed out, the people who are doing these 32-bit fields often do effectively do fry in some extension field of size 2 to 128, but the domain is in this subfield. So this subfield thing just happens all the time in practice. And the problem is what Depenji and Sanso pointed out, which is that there's an obvious part here, which is that if you have a domain that's in a subfield, and then you consider the Reed-Solomon code of this rate for the subfield, this is contained in the Reed-Solomon code of over the larger field. So if the smaller thing has big lists, then so is the larger thing. It's obvious because one is contained in the other, and the list is not going to get any bigger if you add more elements. And as a result, the list decoding capacity bound for the smaller field applies. So that's why we're suggesting HP for characteristic P, because you're if at least for the case where your domain is smaller than P. But maybe your large N case for Ben and Angus's conjecture is enough to get rid of this problem, although it's not so obvious.
About that, I think.
And that's why we're now going to modify this thing to suggest this HP. Dara?
Yeah, so what I'm hearing is subfields are complicated. Would it be fair to say that if you're using sort of central fields, then you should be more conservative and maybe stick to the proven parameters, or
well, I mean, I don't think
it's not conservative.
If you're using like a 2 to the 32-bit field, the binary field case is the really hard one. If you're using this 2 to the 32-bit fields that people use, baby bear and koala bear, etc., then this 1/32 is something you can probably live with.
Well, so you should be more conservative, just maybe not by.
Yeah, you don't need to be incredibly conservative, right? This number will come out fine. You'll have to use less than 1/32 less errors, but if your error rate is already like it's going to already be bigger than that. It's probably you're not going to have row as 1/32.
So, I mean, not to know you, Dan, because this is very complicated, but how confident are you that this is the correct fix for the subfield case?
Right. So I don't think this is. I'm okay. We don't know. Like we made a conjecture 2 weeks ago or 3 weeks ago or something like that, and it's already broken. I say this now, maybe it'll be broken in 3 weeks. But yes, I'm fairly confident. Actually, I'm more worried that we don't have a clue, any sensible sort of maximal conjecture to say for the binary field case. We don't know. But 2 to the 32-bit fields, this conjecture should be fine, and I don't think it's going to be broken straight away.
So
thank you.
I'm going to jump in here real quick, maybe just to ask, since Elizabeth was your co-author, Alistair, since we have 8 minutes left, or 7 now. Elizabeth, do you have anything to add? We don't have a ton of time to go through slides if you prepare them, but I guess maybe I'll just ask at this point if you have anything you'd like to add to the discussion.
Yeah, I mean, I kind of wanted to summarize. I was going to discuss a little bit about where this problem came from, which is actually work on threshold signatures that we did earlier this year. I guess I just wanted to highlight as a summary that basically what we do in our work is disprove the correlated and mutual correlated agreement conjectures, which Ben and Angus also have a nice result on. We also give these improved conjectures. And interestingly, though, basically in this region that we're discussing, this kind of near up to capacity region, we're still not entirely sure that snarks that are operating in this region aren't still secure, in the sense that we basically reduce the problem both in our threshold signatures work and in this work to bounded distance decoding. So Al, yeah, if you just want to jump ahead to that slide. So basically, list decoding requires you to find everything that's in the ball, but bounded distance decoding just requires you to find one thing. So we kind of reduce everything to this bounded distance decoding in that region, and it's possible you could have some assumption there where snarks are still safe and adaptive security of threshold Schnorr signatures is still safe. So I guess we just want to say, as some future work that people might be interested in, to look at this bounded distance decoding and in particular quantum attacks. And then if so, we do have an attack if someone proves something there. And I just want to say also that if somebody proves something about bounded distance decoding, not necessarily for the field sizes for snarks, but maybe for the threshold Schnorr, they would actually also be showing a very interesting separation result between static and adaptive security. So it's like a long-standing open problem in MPC as well. So I just want to plant that seed that anybody who's working in this space, if you want to take a look at this adjacent space of bounded distance decoding, that would be really helpful on a number of fronts, not just for snarks. And yeah, that's it.
Yeah, there was two more things I wanted to explain. Yeah, one of them was this one. I can try and give some detail, but the other one is that we have two more results in our paper beyond the one that's equivalent to Bennett Angus. This one of which is that list decoding, the failure of list decoding implies the failure of correlated agreement, which at least for some parameters. The other one was this subfield question we were just talking about. So Fenzi and Sanso were having a big discussion of the consequences of list decoding failing in this example. Well, correlated agreement also fails, which isn't too surprising. Like these things often fail at the same time. But yeah, the bounded distance decoding issue. So yeah, if you want to actually forge snarks with this, which is what Justin was asking about. So what you typically have is you have something like some quotient that, you have something that should be 0 on some domain. Here's not the, is a conflict with the domain for the code. This could be a different D. You have a snark, you want to prove some polynomial expression disappears on some domain, and then you're sound, but to prove anything else, you can get it something unsound. So now you have something which is a rational function and not a polynomial. But if you're taking some linear combination of that with other words, say random words, this gives you something which is a combination of something that's far, and under previous assumptions, it should be far. But maybe there's a nearby code word. The only issue is you can't find it. Can we actually find this thing? There's no algorithms. So basically, yeah, this problem is bounded distance decoding. It's one element from the list. The list decoding fails beyond the list decoding capacity. The listed exponential, but maybe finding one element is easy. But we really have no clue. There are hardness results. Absolutely none of them cover the case that's interesting. And we're not even sure that NP hard is useful. There are plenty of problems that are NP hard in the worst case, but the average case is easy. And there's one person one paper that did something on discrete logs for extension fields, which isn't post-quantum, but it also doesn't really apply. It's more useful, but it still doesn't quite apply. We really have no idea about whether bounded distance decoding of random words is hard or easy. It looks hard. Yeah, that's all I wanted to say.
Awesome. Well, that was an amazing wrap, Elizabeth. Thank you, and then Alistair, thanks for adding the comments at the end there. I know actually Antonio, who you referenced a couple of times, was on. He who wrote another paper on this topic was in here and then left. Justin's still in here. I know Antonio's doing stuff at the EF, so I don't know, Justin, if you have anything to briefly about that paper. No, Justin's got something else to add. So then I'll just read it. To the 4 authors, besides working on attacks, are you also looking to improving provable security? So I'll let you guys answer the last 2 minutes and then we'll wrap.
In my case, no, it looks really hard. I might actually have conjectured some of the things that Guruswamy and Goyal actually proved. But now they proved it, I really have no idea.
Yeah, I think I'm the same as Alistair. I mean, I'd love to extend the proven security gap. Like there is still this large gap between 1 minus root row and other things, but it's yeah.
Unfortunately, not personally. I think the latest result from Swastik et al. Is quite good in that direction. So outside of us, there is stuff getting done, but I'm not doing it right now.
I noticed another paper relevant to the hardness of bounded distance decoding. I don't know how it relates to the other ones, or whether it's for the right parameters. Just posted that in chat.
See, I mean, just a very quick note on this. So I know that often when people ask about these things, the place that everyone likes to point to is the that eat-stark mini example, and basically about can you break the conjectures there? And I think it is probably worth noting that like if you give like us control over like picking some slightly unrealistic parameters, I think you can actually use Ben and my attack to slightly get to sort of break the E-star conjecture. Like so, like this attack, like there are weird sort of regimes where even though BDD is very hard in general, if your code is low, if your code is low, well, K is low. If your code sort of dimension is low, then it's actually not too bad.
Cool.
I mean, this seems odd. Like the list decoding failure relies on the. So the argument is that the number of combinations is very small, and so it can cancel out your probability being small. When your list of combinations is so large, like we need this thing is not going to work.
I mean, I can copy my attack into chat if you want. Like, it is a very silly attack in some ways because it like we set Q to be small, we set N to be like this, basically the size of Q. But the point is that like you can actually like when K goes to 1, you can actually just go and compute these things sometimes. Like I'm not claiming this attack actually works in realistic parameter settings, but like it's certainly not true that these attacks are necessarily uncomputable in all cases.
Right, just in the real examples.
Maybe to summarize, because we got to wrap up here. So maybe I'll just say, because Justin asked the question, hey, is this a non-constructive or constructive type of attack? And I guess like the answer is, I mean, bound for, the conjecture, the original conjecture is just disproven. The bound has been moved lower. In certain maybe cases, there are reasons to believe that an attack could be made constructive using exactly the technique you pointed out, Angus, or some variant of it. But in general, as Alistair and Elizabeth, I think you guys pointed out, there's still kind of a lot of open questions about how these things are employed in practice realistically and the parameters that are used.
So I think there's something, sorry to interrupt. There's something to be said on this constructive thing, which is that if I take a deep hole and 10 or let's say 100 completely random words, and I let the proximity parameter be something where if the proportion of random words that are close is if I can bound that from below, and I can, it's a constructive but random attack where you don't know which one is the one that actually attacked it, but it's still constructive. It's just a so-called Las Vegas algorithm that will only.
It's more that we have this close thing. If I'm actually trying to like, I do this combination and now we're doing fry with it. In order to do fry with it, do I need to know what the polynomial is that's close? Probably. Without that, things get more difficult. Again, we do some more combinations, and I need to.
Well, first of all, are we attacking fry or are we attacking a snark or are we attacking? I mean, it matters. But
What the naive thing to do here with this proximity gap failure is with this snark. What you do is you have a bunch of things which are supposedly polynomials. I take a random combination of those, and then I do a low degree test on just that.
Sure.
Or maybe several random combinations if my soundness isn't good enough. And for this specific thing, you would need to be able to then do fry on the result. And for that, it would work if you knew what the nearby code word was. It would be a low degree polynomial. You can go and do fry, and you just have to hope that your test for the
in order to
combination was never queries one of the things which is where you are far away, where you're not equal. Yeah.
Also, so if a component fails, then people are not going to want to use things based on that encoded component, even if there is not a feasible attack. So in some sense, for the problem of designing schemes and designing parameters, so the fact that you can't find an attack on the snark, if that is the case, doesn't matter. You want the or whatever it is.
Ourselves live off the fact that the attack was not known, and
yeah.
in other words, you like insecurity. in this.
conjectures that haven't been proved in general.
Guys,
Yeah, well, I feel like one takeaway is you should like this is I guess Ben and my point. I think that we tried to emphasize was that I think a reasonable takeaway from all these papers is that you should try and use proven security.
Sure, I guess this gets philosophical. And is anything proven in cryptography? Does P equal NP, right? But I think that, you know, if there's any takeaway from this, Angus and I have been shilling the proven security regime, but you can take that for what you will.
well, no, I mean, I'm going to wrap up here. Thank you, everyone, for joining and all the authors. I appreciate you guys being flexible in this a non-standard format, but I thought it was a very good discussion. It was really interesting to hear different perspectives. And I think it illuminated this topic, which, I mean, hopefully as the audience can see, I mean, this is a very dense topic. And in many ways, I think this is like these boundaries are not well understood, and the complexity that, you know, that oftentimes these systems contain when they're deployed, you know, maybe is not as secure as we potentially believe. And there's a lot more work, as Elizabeth, you hinted at, to potentially go down and learn more about that. And it sounds like there's a bunch of other papers and authors we should invite on the next iteration of zkStudyClub now that we're picking it back up. So with that, I just want to say thank you very much to everyone for joining, and thanks for taking the time, and thank you to the authors for presenting today.
Thanks,
Yeah.
Alex. And
I'm really glad that we are picking zkStudyClub back up. It's one of the most enjoyable sort of deep tech things that I watch.
I know, Darryl. I've enjoyed the chance to see you again and have the benefit of hearing all of your very intelligent questions. I think that's the thing I've missed the most personally, is that I didn't have that before. So thank you for participating, as I counted on you too for this one here. All right, thanks everybody.
thank you.
See you.